Now that we've discussed the evidence for the continents having moved, we're going to discuss the theory and the types of boundaries and landforms that form it. First, we have Alfred Wegener. He's credited with being the first to come up with the idea of continental drift in roughly 1912. He theorized that the continents have moved or drifted from one location to another over time, floating on deeper, more fluid layers. His evidence were fossils and mountains, glacial deposits and rocks on different continents that match up, showing they used to be attached in the past and have moved since. However, his theory was rejected because he couldn't explain how the continents moved. What force on Earth is possibly strong enough to explain how Africa and South America split up and moved so many thousands of miles apart? Later, after World War II, this was replaced with the plate tectonics theory, which explains that the crust holding the continents are moved by convection cells in the mantle and something called slab pull. These diagrams show what this means. The core is extremely hot, and thus in some areas it heats up the lower part of the mantle, much like a stove heating up the bottom of a pot of water to boil it. The heated material rises towards the surface. Here we have a close-up view of the surface. The heated material rises, some of it pops through, but most of it actually moves to the side. So the heated material floats to the surface, cools, and then sinks. This is called a convection current or a convection cell. This motion, this movement, drags the crust along with it. That would be a convection cell. Also, we have slab pull. You see, as the crust, which is created at the mid-ocean ridge here, from magma that comes up to the surface, is cooled and solidified, this crust moves along, and as it does move, it cools off, and becoming cooler, it becomes more dense, and thus eventually will sink down into the mantle, and be destroyed. But as it sinks, the weight of this slab pulls on the crust, pulling it deeper and deeper in, dragging it along the surface. Thus, these two forces, slab pull and convection currents, create the motion of the plates. We end up with a map that looks like this. This map shows the 16 major tectonic plates, including South American, African, Eurasian, North American, Cocos, and Nazca, and also shows their relative motions. If the plates are moving, obviously some places they're moving apart, others they're sliding past each other, and in other places they are colliding. And all three of these have names. When they move apart, we call it a divergent boundary. I think of it as dividing. It is splitting apart. Where the two slide past each other, it's called a transform boundary. I think of Transformers. You know, those toys that children play with that convert from, say, a semi-truck to a robot. The pieces slide past each other to change. That's transform, sliding. And finally, we've got the crashing together, and this is called a convergent boundary. Con is with moving together towards each other. First, we're going to discuss divergent boundaries. These are where the two plates moving apart, and it's called a tensional force. If you've got tension on something, they're pulling apart. The magma rises from below and produces something we call seafloor spreading, because it often happens in the seafloor and spreading out. If it occurs in the continental crust, it produces a rift valley. Rift, again, means splitting. And in the middle of the ocean, it's called a mid-ocean ridge. In all of these places, new crust is created. Brand new crust born today. This animation shows a divergent boundary just forming. The two areas are pulling apart, and as it does, it stretches the crust a bit. And magma from below begins to melt it just a little bit until you get a volcano. These broken pieces of crust, they're called fault blocks, fault block mountains. Ultimately, the crust thins out enough, it produces an area where we produce, this is a mid-ocean ridge, and a brand new oceanic crust is formed. And we have a continent over here, such as, say, Africa, and on the left we have a different continent, such as, for instance, North America. The two are splitting apart, and beneath it, between it, this would be the proto, or the early Atlantic Ocean forming between them. Here in Google Maps, you can see a close-up view. Here is Africa, South America, North America, and this is the mid-ocean ridge. It's, if you think of it as a scab running down through the center of the ocean, where the Earth's blood, magma, is erupting towards the surface and solidifying to make a scab, that would actually be a fairly accurate representation. You see it's kind of broken in some parts where it's splitting faster in one location than it is in another. It's a very jagged scar, but it is an area where the two plates are moving apart. We actually can measure geographically through GPS units from here to here, and we measure periodically and find that we are moving away from Africa at a rate of 3 to 5 centimeters each year. So it's kind of neat we can actually measure that happening even right now. And these are more, prosaic images. Here you've got the mid-ocean ridge. Lava comes to the surface, produces that scab, that raised mid-ocean ridge. And this is a very young rift valley. For instance, there's one in Africa, the Great Rift Valley. Africa started to split up a bit and stretched a bit, but it's what we call a failed rift. It didn't split all the way. It started to, but the forces beneath it weren't quite strong enough to split it apart entirely. Next we have a convergent plate boundary. These are where two plates are moving towards each other, and it's due to compressional forces. It's being crushed together. And since we have two different types of crust, ocean and continental, we have three different types of convergent boundaries. We could have two oceans crashing, two continents crashing, or one of each. And that's what these images show. Two oceans crashing, two continents crashing, or one of each. When an ocean crashes into an ocean, we call it subduction. Sub, of course, means under. So it's when the more dense plate sinks under the less dense plate and melts. And that's what you see in this side view. One piece of the oceanic crust, one plate. For instance, this could be the Pacific Ocean plate. It's a little bit older and more dense than the North American plate it's crashing into, and so when it crashes into it, it sinks under and is destroyed. What's produced is a trench. Here is where this crust is sinking under the other, and it bends down and produces this long ditch, if you want to think of it. Now, when it sinks under, it's just the rock. It's not the ocean itself, but the rocks at the surface are a little bit wet, so this speeds up the melting process. And so as it sinks under, it melts, it bubbles up to the surface, producing these volcanoes. Since it's sinking under not just at this one location, but all along the edge of the plate, you get a long row of volcanoes parallel to the trench. Eventually they stick up above the water and thus produce islands. This would be the Japanese islands, the islands that make up the country of Japan. This is also what makes up the Philippines. Finally, these produce earthquakes. These yellow dots are meant to relate to the earthquakes. Earthquakes happen whenever two rocks rub up against each other. Right at the trench, the rocks are close to the surface. This crust here is rubbing up against shallow rocks, so it's called a shallow earthquake. And we can actually, whenever an earthquake goes on, measure the depth of the earthquake. And right at the trench, it is very shallow. And it gets gradually deeper as you move away from the trench. So this allows us to actually map and see how steeply this crust is sinking. Some places, the crust may only be sinking, it may survive out to here. Other places, it sinks much faster. Some places, it sinks somewhere in between. But we can actually look at the earthquake data to see exactly what angle this crust is being sunk under and destroyed. and it is destroyed. The crust is destroyed at this location because it is melted into the mantle. This is part of why the ocean crust is never very old, because it is constantly recycled. When two continents collide, it looks much different. It's what we call a collision, crashing together. Neither is dense enough to sink, though, into the mantle. So they both stay at the surface, and it looks a lot like a car crash, and you get the crumple zone. And these are their mountains. The Himalayan mountains are produced this way. They're actually getting higher every year as India crashes into the rest of Asia. And the Appalachians are a sign of an old collision between Africa and the United States. They're folded mountains. It also produces earthquakes. However, you'll notice that the crust is so thick here, there's no magma rising towards the surface, so there are no volcanoes. This is a Google map image of the Appalachian Mountains, and you can see here the wrinkles in the land. And this is what a folded mountain range looks like. And it's almost like you had you put a tablecloth on your table, and then you pushed it in against it from the side, and it produced these long wrinkles. But the rocks themselves have been wrinkled, and that's what the folded mountains are. Next, we get an ocean-continent collision, and this is a lot like an ocean-ocean collision. We still get the ocean trench. We still get earthquakes, shallow near the trench and deeper further away. And we still get lava boiling up towards the surface as the ocean crust melts. And it is always the ocean crust that loses the battle. Continental crust is too low density to sink. But in this case, since this is a continent, the volcanoes are on land rather than in the ocean. So it produces a volcanic mountain range. Crust is still destroyed, but it's only the ocean crust being destroyed again. Here's the Google map image of this happening. This is the Nazca Plate, part of the Pacific Ocean, makes up part of the floor of the Pacific Ocean, and it is moving this way towards South America. And as you see, notice this deep, dark area. That's a trench. What's happening is that this crust is getting sucked underneath this crust. So as it does, it sort of bends downward, much like the bottom of a conveyor belt, and is sliding underneath, and it's actually kind of neat. And as it's sucked under and destroyed, it melts, bubbles up towards the surface, and you can see this mountain range. These are the Andes Mountains, and it's a pretty high mountain range, and it's all volcanic, and it is also extremely earthquake prone. Some of the most powerful earthquakes ever measured have been in this area. Finally, we have transform plate boundaries. These are where two plates slide past each other. It's called a shearing force because, just like shears, scissors, in this image, the two pieces are sliding past each other. If you picture scissors, they don't actually crunch into each other, the metal would break. Instead, they slip past each other, and that is a transform boundary. For the rocks, it produces earthquakes. So like in this area, here we have the Pacific Plate is moving relatively northwest, and the North American Plate is moving relatively southeast. What you may not realize is that LA is actually part of the Pacific Ocean Plate. I know, it's on land. You have a hard time thinking of it as part of the Pacific Ocean, but it truly is. The rock of the Pacific Plate actually comes up here towards the surface to produce part of southwestern California and the Baja Peninsula of Mexico. So this is actually moving with the Pacific Plate northwest in comparison to the North American Plate. LA is not part of North America, geologically speaking. San Francisco is right on the fault. Very poor planning on someone's part, but they didn't know at the time. So earthquakes often happen in this region that can cause immense devastation for this poor city. The 1908 earthquake, for instance, virtually destroyed the city, but humans being stubborn, we rebuilt it. But there are no earthquakes in this region. There are lots of earthquakes in this region, but there are no volcanoes in this region. They're just slipping past each other. There's no volcanoes, no mountains, nothing's being built, nothing's being truly destroyed, geologically speaking, just the stuff we put on top. It's just producing earthquakes. And thus you have the entire map of the world broken into plates, some splitting apart, some sliding past, some colliding. This fast little animation is what we're going to close with. This is going to show you how the continents have moved around through geologic time for the past 700 million years as we have tracked them using rocks. Unfortunately, it's rather fast for 700 million years. But watch that go. Isn't that neat? All of that sliding around, moving around, crashing, splitting, developing. This is plate tectonics. North America. Here's Africa, and this is India, breaking off Africa and then crashing into Asia relatively recently.